in the last lectures, we discussed about the characteristics of optical fiber, and then we also studied the signal distortion on optical fiber. In this lecture, now we study the practical aspects of optical fiber, that is, how do we handle optical fiber and what kind of measurements are to be carried out on optical fiber before the fiber is accepted and commissioned into a system. So, just on simpler note, even a cutting of optical fiber is a rather tricky issue. As you all know that optical fiber has to be connectorized, that means at the end of the fiber a connector has to be kept. But before that the fiber has to be cut so that it can be inserted into the connector appropriately. And what you will notice is that if the surface of the tip of the optical fiber is not flat, then there is a scattering of light from that. So, light does not come in a systematic form of beam from the tip of the fiber, and because of that you have a loss when you try to connector this fiber, or if you want to join these two fibers which are cut. So, normally what we do is we essentially take the optical fiber, make a small gentle cut with a blade, and then pull the fiber very gently, so that the crack which you have got with the blade slowly develops along the crystal surfaces, and you have a reasonably flat cut at the tip of the optical fiber. After this also, the fiber tip has to be taken and it has to be what is called polished. So, there are certain polishing cards on which the tip of the optical fiber has to be very gently rubbed, so that the surface becomes reasonably flat. So, this process is what is called the cleaving of the optical fiber. Once the fiber is cleaved, then invariably you have to join the fiber, and that process is what is called the splicing process. There are various types of splicing which could take place. One could be very temporary splicing, that means I have two fibers which I just temporarily want to connect, and frequently we should be able to disconnect also. So, this can be either done by using connectors. You can connect the two fibers or disconnect them, or you can insert two fibers in the form of some kind of a rubber tube, and when the fiber come inside the rubber tube and just get aligned and touch each other, the light can be guided from one fiber to another fiber. So, there is a possibility that without actually making a permanent joint, one can couple light from one fiber to another fiber. Of course, since you do not have any permanent joint for this fiber, there is a large loss in this kind of joint. So, normally if you want to have a good efficient launching of the fiber, and if the joint need not be of the temporary nature, then we normally go for what is called the fusion splicing. So, idea here is if you take these two fibers which come, whose tips are cleaved, so you have got reasonably flat tips, you bring them close to each other, and then this process of joining by fusion is identical to the soldering process in electrical circuits. So, in electrical circuit also, if you want to join two wires, you bring them together and essentially you put a solder, and then you make a permanent joint at the tip of the wire. Precisely same thing we do here, that the two fibers are aligned perfectly, and then a arc is passed at the joint, so that momentarily the glass melts, and at that point of time if you give a small push to the fiber, essentially the two semi molten glass tips of the fiber fuse into each other and you get a permanent joint. So, typically whenever we want to have the joints, and if the joint is of permanent nature, then fusion splicing is the one which is preferred. You can also have the joints which could be UV cured kind of joint where the fiber ends are dipped into some kind of a liquid, and if the liquid is exposed to the X-rays, the liquid solidifies. So, you get a temporary kind of joint at the tip of the fiber. But fusion splicing is the one which is predominantly used whenever we have the network laid for long distance communication. Now, when we are doing this kind of a joining of the two fibers, there are possibility of mechanical misalignment between the two fibers. So, either the fiber could be laterally misaligned, that means the two tips of the fiber may not be, axis may not align, the axis may be slightly displaced, one possibility. Other possibility is that there may remain a small air gap between the two tips of the fiber, and this is more common in that temporary joint which we got with the tubular pipe, the rubber pipe. Third possibility is that there may be a small angular misalignment between the two fibers, and each of this essentially gives you a joint loss. In this case, you can easily see, since the cores are not overlapping, the entire energy which is coming from this core is not guided into the second core. So, you get a loss here. Here you are having a small air gap. So, the numerical aperture cone which comes out of this completely does not overlap with this fiber. So, the part of the energy essentially leaks out from here and we get a loss. In this case, again the same thing, that numerical aperture cone goes like this, whereas this cone can receive energy from this cone. So, you can get a loss if there is an angular misalignment between the two fibers. So, in a practical system, whenever we try to make a joint, we can get loss due to any of these three things. And here is a comparison of misalignment effects. So, we have got here the loss in terms of dB as a function of normalized offset or the separation between the two tips of the fiber. Now, here it is normalized with respect to the core radius. So, you can see here that if the two fibers are laterally misaligned by the core radius, there is a substantial loss of power, and if the two cores are not overlapping at all, that means there is a misalignment by 2A, then no power essentially will get inside the second fiber. So, this is the loss which increases very rapidly as the misalignment parameter. So, that is what this is. So, this shows you the loss in dB as a function of the misalignment. So, by the time you get a misalignment of 1, that means a misplacement of 1 radius, the loss will be of the order of about 3 to 4 dB. The angular misalignment loss is a rather milder loss, which even if you are having a substantial misalignment in terms of theta, which is given here, and this theta is in terms of the numerical aperture normalized to that. Third one, when you are having a separation, you get a loss, but this is the mildest possible loss. So, even if you have a separation of the order of about 3 to 4 radii of the core, the loss could be still of the order of about 1 dB. But in any good system, normally these losses are minimized. So, whenever we do a splicing of the fiber is aligned perfectly in all respects, as per the separation loss, as per the angular misalignment loss or the air gap loss. So, a typical splice loss could be of the order of about 0.5 dB to 0.1 dB. So, technology today has matured in splicing the optical fibers, and as a result you get a very good performance at the joint with loss as low as something like 0.05 dB. And the splicing machines have also become now automated. So, one does not have to worry too much, simply two fibers are inserted inside the splicing machine. The splicing machine automatically does these alignments, and it does the alignment essentially by launching light from one fiber to another, and it adjusts the parameter with the 6 degrees of freedom, so that the light coupled is maximum, and at that instant of time essentially the arc is passed and the fusion splicing takes place. So, this technology is now a pretty mature technology. The next thing which we want to do on optical fiber is the measurement of parameters of optical fiber. And we have seen the optical fiber has certain characteristic parameters. Its first parameter is the numerical aperture. Next parameter is either its V number or mode field diameter. But the most important parameter for optical fiber is its loss. And this loss, as we know, has two components. One is because of the intrinsic characteristics of the fiber, and second one is because of the environment in which the optical fiber is laid. So, you have to make the measurement of loss basically in both the situations. So, let us first say that I want to measure the numerical aperture of the optical fiber. This could be a very simple experiment. We know that numerical aperture is nothing but the sine of the angle at which the light ray can be run inside the optical fiber. Now, whatever cone is launched inside the optical fiber, the same cone also emerges from the tip of the optical fiber. So, what we do? We have a source here. We launch the light inside the optical fiber, and from the tip of the optical fiber, the light comes out. This comes in this form of this cone. We can project this cone on some screen at a distance x from the tip of the fiber, and we will get a spot of light of diameter d. Now, this angle which we have here, this angle is double of the numerical aperture cone. So, essentially what we want is the half of this angle. That is what gives you the sine inverse of the numerical aperture. So, if this diameter of this is d and if this distance is x, the d upon 2x tan inverse, that is the maximum angle at which the light rays could be launched inside the optical fiber. So, sine of this quantity theta max, that essentially gives you the numerical aperture. So, numerical aperture is equal to sine of theta max, and theta max is tan inverse of d upon 2x. So, you can substituting into this, we can get the numerical aperture, which is d upon square root 4x square plus d square. So, by measuring the diameter of the spot which is created by the emerging light from a distance x from the tip of the fiber, one can calculate the numerical aperture of the optical fiber. So, this is a simple experiment which one can conduct on the optical fiber, and since we are doing the measurement here by measuring the spot size, essentially one can use the light source which could be visible light source. So, typically a red light source of helium neon laser can be used, and the numerical aperture of the optical fiber can be measured. So, this is one of the first parameters which one can get. One can also get from this experiment what is called the mode field diameter. If you had a single mode optical fiber, so instead of just measuring the spot size, if you have an optical sensors which could measure the intensity distribution, we can move that probe on the screen and essentially find out the variation of light intensity as a function of radial distance in the spot. So, we can create essentially that distribution which the single mode optical fiber creates, which is very close to Gaussian distribution, and from there we can get the parameter what is called the mode field diameter. Now, since the mode field diameter is a function of wavelength, essentially one can carry out the measurement at certain wavelength and then appropriately scale the mode field diameter to the other wavelength approximately. The third thing which is, as I mentioned, important parameter is the loss. Now, since the loss is because of two parts, one is intrinsically in the optical fiber and other was into the system. Normally, before the fiber is commissioned, the loss in the optical fiber can be calculated. And there are two techniques for calculating the loss in the optical fiber. One is a destructive technique, and this technique can be employed only before the fiber is commissioned into the system. The other technique is non-destructive, and this technique can be used even after the fiber is commissioned into the system, and also during the running of the fiber, during the operation of the fiber, this equipment can keep monitoring the status of the optical fiber. So, first method, which is destructive and which can be employed before the commissioning of the optical fiber, it is what is called the cut-back technique. Now, idea here is simple. Firstly, you have an optical source here. You put the light inside the optical fiber, you measure what is the output. From there, you can find out what the corresponding loss would be. So, if I know the power which is put inside the optical fiber, if I know the power which is coming out of the optical fiber, the ratio of these two powers will give me the attenuation. So, if I knew the fiber input, so if this is my fiber, I put a power here which is P in, I get a power here which is P out. So, I can get the attenuation constant alpha, which is nothing but 10 log to the base 10 of P in by P out. So, principally this method is very simple. Essentially, we measure the light which is going inside the optical fiber, the light which is coming out of the optical fiber, and just by taking the ratio of that and log gives you the attenuation in dB for the optical fiber for that length. If you want to have the attenuation constant in dB per kilometer, you can essentially divide by the length of the fiber. So, this is L in kilometer, I can divide by L. So, you get loss of the fiber in dBs per kilometer. Though principally this technique is very simple, in practice there are certain difficulties, and the difficulty is that normally when the light is launched inside the optical fiber, at the launching point there are substantial losses because of scattering of light. So, though this quantity can be very reliably measured, the light which gets inside the optical fiber is not a very reliable parameter, because even if I knew the source of light and how much power is coming from the source, how much light actually get inside the optical fiber is still a very uncertain parameter because of the coupling losses. So, as a result, although in principle this thing looks a very simple process, you cannot really use this technique in this form because this quantity is very unreliable. So, normally what we do is we use this method, what is called the cut-back technique. So, you take a very long length of optical fiber L, launch the light inside this, and there is a device which is called here the mode stripper, because when the light is launched inside the optical fiber at the launching point, you have a large number of modes which are generated, which very quickly die down, and finally the mode which are well confined to the optical fiber which propagate. So, you have a certain distance here which guarantees that. Now, you measure the light output after the light has passed through this fiber. That is the quantity which is P out. Then what you do, you simply cut the fiber over a distance of about 10 meter or something like that, and you measure again the light which is coming out of this point, which is what is called the near end of the optical fiber. So, if this length is typically of the order of about a kilometer or something like that, loss of the fiber over a distance of few tens of meter is negligibly small. So, then we can say that whatever light comes out from this point, the near end of the fiber after the fiber is cut, that is same as the P in for this fiber. So, we do the measurement of light coming out only. In first case, with the full length of the fiber present, you get that, which we call as P out. Then you cut the fiber here near the near end of the fiber, and that P out is essentially P in. Then getting the ratio of these two, you can use this formula and you can get the attenuation constant of the optical fiber. So, before the supplier gives you the optical fiber, this method can be employed, because as it is very clear, you have to cut the fiber. So, this method cannot be employed after the fiber is commissioned into the system. Otherwise, this method is a reasonably accurate method if you can afford to cut the fiber, and that can happen only before the installation of the optical fiber. The very powerful technique which can be employed to estimate the loss of optical fiber before and after commissioning of the optical fiber, what is called the optical time domain reflectometer. So, what we have here, we have a device what is called the optical time domain reflectometer, which is nothing but an optical radar. So, you recall in radar what we do? We essentially send a very narrow pulse of radio wave. The pulse goes, it gets reflected or scattered from the object. The echo of the pulse you receive back, and then from the echo essentially we get two parameters. One is the delay of the echo, that means the return time of the signal, and second one is the amplitude of the echo, which tells us from what size object the signal has reflected. So, from these two parameters, then we estimate the size of the object and the distance of the object. Precisely same thing essentially we do in this device, what is called the optical time domain reflectometer, or in short called OTDR. So, this OTDR has basically components like this. It has a laser source which launches the light. Then you are having a beam splitter. So, the light passes through this. This goes inside the fiber which is to be tested. The other end of the fiber is not needed now. So, light which goes inside the optical fiber, because of the scattering or reflections at various points, the light gets reflected, it comes back. The return light is diverted through this beam splitter in this direction. You detect that light and plot that on the oscilloscope as a function of time. So, if you launch a very narrow pulse of light, what you will see is that we do not have only one echo which will be coming from here. The echo will come from different points. So, some energy may get reflected from here, some may get from here, some may get from here. So, what we see is that the signal which is getting reflected from various points will arrive at different times. So, it will have a different location on the oscilloscope screen. So, for a very narrow input pulse given from here, you will get a signal which is much spreaded in time. That is what will appear on the oscilloscope. So, the maximum time separation or spread which you will get would correspond to the maximum return time which you can get on the optical fiber. So, note here, if I had an optical fiber of length L, a pulse is launched from this. The pulse will go all the way up to this point and come back. So, it travels a distance of 2L, and if the velocity of the light inside the fiber is C divided by N, where N is a refractive index, or we can call N effective if we are having a fiber which has refractive index N1 and N2 for the cladding and core, then the delay maximum which you get from here, that will be equal to this 2L divided by the velocity, which is c by n effective. So, for a very narrow pulse launched inside the optical fiber, we get a reflection which has a time spread of T max. So, typically that is the spread over which the signal will come from 0 to tau max. Now, one can ask a question now that when the signal goes inside the optical fiber, why do I get a reflection? And you will recall that inside an optical fiber we had these micro centers which were giving you the scattering loss. We can now rely on those losses, and as we know that scattering loss is because of the scattering of light which takes place in all directions. So, as the light goes inside the optical fiber, a very tiny fraction of that light gets scattered in all directions. So, part of that light essentially will travel backwards inside the optical fiber. That is the light essentially we are trying to capture. So, now the pulse, when it goes into this, for a nice uniform fiber, the scattering loss or scattering mechanism is identical at every location on the fiber. However, if you ask how much will be the scattered power, you will see the scattered power will be proportional to the local power density at that point. So, what that means is that initially when the pulse is launched, if the scattering takes place here, you will have a much larger amplitude of the scattered signal than if the same kind of scattering takes place here, because by the time the signal reached here, it would have attenuated because of the loss in the optical fiber, and then whatever scattered light you get from here is further attenuated as it travels back. So, the reflected signal or scattered signal which you get from near end of the fiber is much stronger compared to the far end of the fiber. And in fact, the ratio of these two scattered light is proportional to the loss in the optical fiber. In fact, proportional to twice the loss in the optical fiber, because the pulse is going to get attenuated by attenuation constant. The scattered light is further going to get attenuated by the same attenuation constant. So, the reflected signal will be doubly attenuated. And that's the reason you see that in this time spread, you do not get the scattered amplitude which is constant. The scattered amplitude essentially monotonically decreases if you are having a nice uniform fiber, because at the near end you get a much stronger reflection, and the farther end essentially the reflection is very small. So, if you take this trace of the oscilloscope, the typical trace would essentially look like that. So, oscilloscope display or what you call OTDR display essentially would look like that. So, if we had a fiber which is absolutely uniform fiber, then we will get a trace which will be a straight line if we plot this in terms of the logarithm, in terms of dBs, because dB per kilometer will be constant, and slope of this line essentially will be equal to 2 times alpha, because the signal is attenuated and the scattered light is further attenuated. So, just by measuring the slope of this line, the trace, essentially one can calculate the attenuation constant of the optical fiber. But now let us say that the fiber is not absolutely uniform. Let us say the fiber had a joint here and I had another fiber here. So, at this point there is a junction, maybe there is one more junction here or there is a connector here. And whenever we have a junction like a splice or a connector, you have partial reflection of the light from that point, not the relay scattering. This is the partial, what is called Fresnel reflection, which takes place from these joints. So, you will see suddenly at this, from the signal which is getting reflected from this point suddenly has a large amplitude, because at this point suddenly more amount of light is reflected. But beyond this point, since now the light amplitude is reduced because more light is reflected, the signal level of the scattered light will drop compared to what it was here. So, typically you would see that you get a trace on the OTDR which will look typically like this. So, firstly, at a very short distance you will see a very strong peak, and this is the peak because there is a reflection of the laser beam from the tip of the fiber where the light is getting launched inside the optical fiber. That is this peak. Then inside the fiber you get the scattered light which has a slope which is equal to 2 alpha. At this location you again have some joint or something, so you have a Fresnel reflection, and as I mentioned, beyond that again it drops because now more light is lost in this process, and like that you can have some small imperfections. So, a typical trace would essentially look like that, and these points where you see this abrupt changes into your trace, these are the locations in the fiber where either there are connectors or there are splices or joints, or there are some other imperfections inside the optical fiber. And at the far end of the fiber, since beyond that now the fiber is not there, again you will see a strong reflection from the other end of the fiber, which is this reflection. So, typically the trace of the OTDR would look like that. So, OTDR actually can tell you a lot of things. It tells you the attenuation constant of the fiber, which can be measured by the slope. It can also tell you that where the imperfections in the fiber are, where are the connectors located inside the optical fiber, and so on. So, OTDR is an extremely powerful technique for measuring the losses on the optical fiber. And not only losses, it is also possible to essentially monitor the status of the optical fiber. Now, since this method requires access of the optical fiber only at the input, we do not have to have an access to the far end of the optical fiber. This measurement can be carried out even after the fiber is commissioned, and precisely that is what is done in practice. Periodically you connect an OTDR to the optical fiber, find the trace of the optical fiber, and it gives you perfectly the locations where the connectors are located. But suppose you find suddenly an anomaly into your trace. Let us say suddenly at this location suddenly there was a sharp peak, which normally when you install the fiber was not there. So, you can immediately come to know that there is somewhere tempering or something has taken place to the optical fiber. So, OTDR not only helps in carrying out the measurement of the attenuation constant on the optical fiber, but it also helps you in monitoring the status of the optical fiber during the operation of the optical communication link. And that is the reason this technique is an extremely powerful technique. Now, certain issues one can ask here. Firstly, to get a trace, ideally speaking, one light pulse is good enough. So, if I just send one light pulse, you will get this reflected signal which will look like that. I got a trace, and that should give me all the information which I am looking for. However, note here that the light which we are measuring is extremely weak light because it is coming because of the Rayleigh scattering predominantly. So, for typical light which you can launch inside the optical fiber, if I want to have a substantial reflected signal, we should have two things happen. First thing, the power in this pulse should be very large. That is one. Second thing, this pulse should be very narrow, because otherwise we will not be able to identify the faulty locations the separation will depend upon the width of the pulse. Larger this width of the pulse, more will be the ambiguity in the distance of the two imperfections in the fiber. So, to get what is called the higher resolution of the faults on the optical fiber, you have to make this pulse width extremely narrow. But you want a certain amount of power for detection, because otherwise your signal will not be detected properly. So, as a result, essentially you have to increase the peak power of this pulse, because the average power has to be maintained at a certain level. So, ideally for a OTDR, we require reasonably high power, very narrow pulses, that means with very high peak power. This is what we normally do in other radars also. And these are the pulses which essentially go inside the fiber and get reflected. But as I mentioned, even with that high power, the light which you can receive from one pulse, that is very, very small, and it gets completely submerged into the noise or statistical variation of the signal after detection. That is the reason just one pulse launching will not suffice in practice, because with one pulse you will not be able to get a trace which is like that. So, in fact, if you just transmit one pulse and if you take the signal and plot it as a function of distance, the signal will not have a trace like this, but signal actually will look something like that, something like this, because the signal is completely submerged into the noise. So, what we have to do, essentially we transmit multiple pulses and go on averaging the signal which comes from various pulses, and then slowly the signal to noise ratio will improve, and then the trace of the OTDR will emerge. So, you will get a trace slowly getting emerged from this, because the signal to noise ratio will improve after the integration. That is the reason we have to transmit multiple pulses on the optical fiber for measurement of the loss. So, two issues now come in. When you are launching now the multiple pulses inside the fiber, what should be the minimum separation between these two pulses? Or in other words, what should be the pulse repetition frequency? And secondly, how narrow should be the pulse width for a given resolution on the optical fiber? So, firstly, you will note that for every pulse which is launched, the return signal or echo will be spreaded over a time which is this time, which is tau max. That means, if we had another pulse transmitted within this time, we will not know whether the received signal is because of the previous pulse or the next pulse. In other words, there has to be a minimum separation between the two pulses, which should be tau max, which essentially is given by this. So, if we have the maximum distance given to you, then you can get the repetition frequency for the pulses, which will be essentially 1 upon this tau max. So, you can get the pulse repetition frequency PRF, that is equal to 1 upon tau max. Here L is the distance or the length of the fiber. So, depending upon over what distance one would like to carry out the measurement on the fiber, one can decide the pulse repetition frequency. Typically, one can use this technique for a distance of about 50-60 kilometers. So, you get a pulse repetition frequency which will be extremely small, which will be typically of the order of about few hundred cycles or few hundred pulses a second. That is the kind of pulse repetition frequency you can get. Second thing what we have now is the resolution, and what the resolution essentially is that suppose we had two faults on the optical fiber something like this. The pulse energy will go here, will get scattered, will travel back. Pulse energy will get scattered from here, will get travel back. And the energy which is going to come here at that instant of time, if I see the pulse will have a width which will be exactly same as the width of the launched pulse. So, if we forget about for scattering loss for time being, suppose we had reflection coming from this point and this point. Essentially, we will receive two reflected pulses of its original width, one from this location, one from this location. So, essentially what we will get for the two events or two faults on the fiber, you will get the two pulses which will be reflected, one from here, one from here. So, this is one pulse, this is another pulse, just separated in time. Now, if the two faults are close to each other, these pulses will overlap. So, we can define a resolution is the minimum distance you should have between the two faults on the optical fiber, which can be identified as two faults. If the two faults were located within a distance smaller than that, then the two fault would appear as one fault. So, approximately we can say that the resolution is approximately equal to the half power width of the pulse in time. So, this is the half power width of the pulse in time. So, you can get, if the half power width is larger, you will get a larger separation between these two. So, ideally we want the half power width of the pulse should be as narrow as possible. This width can be converted into the spatial distance. So, you can say that if this was pulse width was tau, then the tau multiplied by C upon n effective, that gives you the spatial resolution. Note, however, that the half power width of the pulse, because of the dispersion present on the optical fiber, is a function of distance on the optical fiber. So, initially you launch certain pulse inside the optical fiber which has some value of tau, but as it propagates on the optical fiber, because of dispersion, this pulse broadens. So, if the pulse was reflected from a nearby location, it would have a width which will be almost same as the width of the transmitted pulse, whereas if the pulse was reflected from a location which is very far away or the far end of the fiber, then the pulse would be broadened because it would travel a distance 2L on the optical fiber. And since the resolution is related to the half power width of the pulse which we receive, in other words, what we are saying is that the resolution will become a function of distance on the fiber. So, the faults which are very close to the near end of the fiber, you will get a smaller resolution. The fault which are toward the far end of the optical fiber, you will have the poorer resolution. So, if we approximately say that the pulse which is launched inside the optical fiber is of Gaussian nature, and tau essentially is the standard deviation of that pulse, input pulse. And let us say the pulse broadening which takes place inside the fiber is also more or less of Gaussian nature. We can say that initially you had a Gaussian pulse with a sigma which is equal to tau I. This is approximately a Gaussian pulse. Now, if I say that the broadening phenomena which is because of dispersion is also Gaussian, and if the dispersion on the fiber is given by d, dispersion is d, and the spectral width of the source is sigma lambda, and length of the fiber is L, then the broadening function would be a Gaussian function with a standard deviation which will be nothing but d into sigma lambda into L. So, we have a pulse broadening function with variance equal to d into L into sigma lambda square. So, when a Gaussian pulse is launched inside the optical fiber, it gets broadened because of this broadening function, which is a function of distance L. So, since both of these functions are Gaussian, the reflected pulse which will be received by the OTDR will be simply convolution of two Gaussian pulses. So, output will be again Gaussian with a variance which will be sum of the two variances. So, you can get now the pulse width for the reflected signal that will be equal to, so that is let us call tau, that will be equal to square root of the variance of the input, which is T I square, plus the variance of the broadening function, which is d into L into sigma lambda square. That is what precisely now we have, that the resolution which we are going to get now would correspond to this pulse width. So, when the length is small, so that this quantity is negligible compared to this width, you will get a resolution which will be decided by the input pulse. But if the distance is substantial, so that this quantity becomes negligible compared to this one, then the resolution essentially will become proportional to this quantity L. So, if we consider a OTDR and if you consider the long distances which are there in the fiber, depending upon the dispersion parameter and the spectral width which we are using for the OTDR source, we will get the resolution of the OTDR which will become function of the length of the fiber. So, now we find something interesting for the OTDR measurement. One is OTDR measurement is extremely powerful measurement, because this measurement can be carried out even after the fiber is commissioned. And in fact, if you can have multi-channel transmission, one of the channel can be connected to OTDR, maybe on permanent basis. So, if anything goes wrong on the optical fiber, immediately you can get an alert. So, OTDR technique can be employed to find out the status of the optical fiber and continuous monitoring of the loss performance of the optical fiber. The OTDR signal, the resolution which you can get on the OTDR is decided by the pulse width which you can launch, and typically a nanosecond kind of pulse is launched inside the optical fiber, but the resolution will be a function of distance on the optical fiber. So, the faults which are towards the near end of the optical fiber, they have a much finer resolution compared to the faults which are towards the far end of the optical fiber. But typically today the OTDRs are of extremely good quality, and one can get a resolution typically of the order of about few meters on the optical fiber. That means, sitting in the office on the console, we can find out a fault location on the optical fiber with an accuracy, spatial accuracy of few meters over the length of the optical fiber, which could be typically of the order of about 50 to 100 kilometer. Therefore, this is a very extremely important tool. So, OTDR or optical time domain reflectometer is one of the extremely important equipments which the people have to use in monitoring the status of the optical fiber. Lastly, the parameter which you want to measure is the dispersion on the optical fiber. So, here the setup is as follows. Essentially, we have a laser diode. You just have the pulse of the signal which you launch inside this, and then you get the signal output, and then you measure simply the pulse broadening inside this. So, idea here is simple. By launching a very narrow pulse, you find out what the output pulse would be, and as we saw in the previous case, the output pulse would be convolution of the input pulse and the dispersion broadening function. So, if you have an estimate of the output pulse, and if you assume that the broadening function and the input pulse both are Gaussian in nature, then one can essentially find out the variance due to the dispersion broadening function. So, by using a setup which is similar to the previous one can also get an estimate of the dispersion on the optical fiber. Many times what we do is, we just let the signal pass back and forth in a short length of optical fiber to emulate a very long distance on optical fiber, so that you can get a large pulse broadening because of dispersion, and you can get the estimate of the dispersion from that. So, in this lecture, essentially we have summarized some of the measurement techniques which are employed in practice for the optical fiber. So, first we saw the numerical aperture measurement, then we went to the loss measurement, and in this we saw two techniques, the cutback method and the OTDR method, and then by using similar setups we could get the measurement of the dispersion also. So, this essentially concludes our discussion on the optical fibers.